hopefully it's almost in a sense boring for how much of a review it is. Okay, so this brings us to conditional probability, which I don't believe we had touched before. Give me a thumbs up if we have touched this before. Good. All right. So I saw most people's faces like, I'm not sure. All right. So I think that for the most part, we haven't really seen this. So basically conditional probability is same thing as probability, like flipping heads or tails. However, we add an extra condition on top of it. And kind of similar, we'll see in a second, like, let's see if I can find it real quick. Oh, here, like this example right here, that little bar, you can think of that as like such that or given that. Kind of similar with when we talk about mathematically. It's like, oh, it's all of X, except X has to be an integer and X has to be, you know, greater than 0, less than 20. That's kind of what that condition is. So that's what that little bar is essentially going to say. But basically our conditional probability, we still have the same sample spaces. We're basically saying, but we're only going to consider this. So I think the example the curriculum talks about in this lesson, they say like, what's the probability of it being sunny given that you're happy? You know, like, and they have basically this probability part. So like, there's a probability of how often it's sunny, but there's also a probability of how often you're happy. It's like, what's the probability of it being sunny while you're happy? That's a new condition on top of it. There's some other parts, you know, you can start adding more and more conditions. That's what we're going to talk about. So there's an important distinction between basically independent and dependent events. So an independent event, basically, hopefully you kind of get the idea, is that independent event doesn't affect each other. So if events are independent, it doesn't matter if I measure one and then the other, or the one and the other. Or sorry, I'm just swapping my words around. It doesn't matter which one we measure first. One doesn't affect the other one. Okay. And what that basically means mathematically, we can say is like, all right, the probability of A and B, basically, right, is basically just the probability of A. Oh wait, this is right. This is wrong. Ignore this part. I'm not sure why I have this guy. Ignore him. All right. So the probability of A or probability union B, sorry. Probability of A union B, right? Oh, I guess that's the same thing. In my mind, it was different. But we have this full event space. And so the probability of this happening, it's just simply the probability of A plus the probability of B. And basically this will help define what an independent event is. It's like, these are things that shouldn't affect each other. Okay. We also have disjoint, which basically is that they're not connected together, which is not the same thing as independence, but they're similar in that way. And so we can see here that basically the form definition is the probability of A union B. So A and B together, okay? It's just simply the probability of A plus probability of B, which you can see visually here. I think this is from the curriculum right here. It's basically, they're just completely separated from each other. So you can just consider those separately. And this is actually a really interesting one because this is actually what we'll see as, if you looked at this equation, for example, you would find that this is called Bayes' theorem. And Bayes' theorem basically allows us to do a lot of conditional probability without having to calculate every aspect. And a lot of times the hard part is figuring out this guy right here. So what we do is basically we can figure out some condition by figuring out other parts of it and we can combine them together. So that's kind of conditional probability. Basically, it's when you say, all right, I'm only going to measure this given that this has already happened. So I only care about how often you're happy when it's sunny. Okay. Hopefully that kind of gives an idea of what condition is. Any questions on those definitions? I think like if I say like verbally like independent versus dependent, you intuitively have an understanding of what it means to be independent versus dependent. Sound about right? Yeah. Okay. So thumbs up right now for understanding, thumbs down, sideways. Okay, I think I have mostly thumbs up. All right, cool. So this kind of leads us to a couple of theorems. This again is put out by the curriculum already, so I'm not going to go full into it. I just wanted to show you really quickly. We have the product rule, the chain rule, and then we'll talk about Bayes' theorem in a second. But basically, the product rule essentially allows us to combine probability spaces together. And this is essentially is that the A intersect of B is just equal to the probability of B times the probability of A given B. Okay, and so this is true in general. It's just that it turns out is that if A and B are independent, okay, that intersection is just going to be simply probability of B by itself, like or probability of A times the probability of B, and that's where we get. I got rid of it, but basically we would get this would simplify further. Basically, the probability of B times probability of A if they were independent, right? So the way I kind of phrase this is that let's see here. If we have A and B is equal to the probability of B times the probability of A given B, what this looks like, or what this could look like, is let's say I have this full event space. I'm going to draw this full event space, and I'm going to have, for example, this is the probability of A, and I think it's, the curriculum actually gives a pretty similar description that looks like this. And let's say this over here, on this on the right, is probability of, or the event space of B. Okay, so we can say like B, probability of B by itself. I'm just going to make some numbers up. We're going to say that that's like 50, like 60%. Okay, basically 60% of that whole thing. And maybe the probability of A is something like, I don't know, 10%, 20%. We'll say 20%. We'll give it a little more. Okay, so these are by themselves. But the thing is, when we would say, okay, well, I want to know what's the probability of A and B, right, intersect of B, right? What that really means is, if I want to actually kind of like highlight it a little bit, what I want is this guy right here. Okay, so the way we can kind of consider this, like, well, okay, how likely is B to happen? That's what probability of B is. Like, okay, what's the likelihood of being in this section over here? It's like, okay, I got this section. And then you say, okay, of this whole section, what's the probability of A happening given that we're already inside of B? Okay, and that's where basically this multiplication comes in. So you can think of it like, if this is like maybe only 10% of all of the B part, essentially what that would mean is that, okay, that would mean the probability of B happening, well, that's 60% times the probability of A happening, given that we're in B, that'd be like 10%. I'll draw the percent so it's easier to say, okay? Which would give us, in this case, what, 6%? That sounds about right. Okay, 6%. And you can see is that that would basically mean the same thing as saying, okay, what if we only considered this portion right here without even thinking of A and B? Okay, and you say, okay, that would be 6%, but this is how we would actually calculate it. So essentially that's what this is giving here. It's like, all right, first consider how likely is B going to happen? And then say, okay, given that B already has happened, how likely is A going to happen? And that is essentially what this is saying right here. Okay, does that make sense? Thumbs up if we're looking good. Thumbs down if we're like, oh, I'm completely lost. Get some sideways here. Yeah, so another way you can kind of think of this is that like, I'm trying to think of a good example on the fly. Let's say the probability of being struck by lightning. Okay, we have this right here. And let's say the probability of us being struck by lightning is this A part right here, right? Okay, so sorry, this is confusing. Let's make it inside there. So this is the probability of A. So the probability of getting struck by lightning is about that small, right? Okay, but the probability of getting struck by lightning, considering that we're wearing a suit of armor, okay? And we'll make this like this. So this is gonna be the probability of us wearing a suit of armor because, I don't know, sometimes we go LARPing or something like that, right? So we're doing something, we don't wear a suit of armor every day, but sometimes, you know, we just enjoy, you know, a good Wednesday and just want to throw on some suit of armor, okay? So this is representing, this B part right here is representing the suit of armor. So what this, if I want to know the probability of me getting struck by lightning and wearing a suit of armor, okay, which seems like not important, but we'll talk about why this is actually a useful thing, is this is equal to the probability of A, or let's say, we can also use this form right here. So we'll kind of go, the probability of B happening, so this is like me wearing a suit of armor, and then multiplying it by the probability of A happening, getting struck by lightning, such that we're wearing a suit of armor, okay? And if I was probably being truthful, you know, like in likelihood, it'd probably be something like this, right? Like most of the time when you get struck by lightning, it's because you're wearing a suit of armor. We're just gonna make this world up. But basically right here, it's like, okay, what's the probability of us actually wearing a suit of armor? Okay, it's like, okay, we wear it like, you know, like 30% of the time because we really like our suit of armor, okay? we just left it to where everywhere we can. Okay, and then probability of A such that B happening. Well, it's like almost a 90% chance, you know, if we're wearing it. Like, well, not 9% chance, but like there's a very high chance of us getting struck by lightning given that we're wearing a suit of armor. So this would give us another probability. So we'll say something like, oh, that's something like around like 60%. Okay. And that would give us the probability of this whole thing together. And so that's essentially what this is saying. It's like, okay, first give me an event that happens, and then given that event happens, how likely does this happen? Okay, and this will give us the whole intersection. And usually what's interesting is that usually we know how to do this part. We don't really know what this is. This is usually the question mark. And essentially what we'll usually phrase this as said, is in Bayes' theorem, is we'll say probability of A given B divided by the probability of B. So it's me trying to write on the computer, is equal to the probability of A such that it's the probability of B. Okay, and that's usually how we'll write it, kind of deal. And what's interesting is this allows us to do calculation a little bit easier. Usually we can determine these parts over here or another form of it by essentially just doing experimentation and measuring, and we can update our thing, which is called our prior and our posterior. Okay, and again, we could solve this directly from these parts right here. Okay. If we simplify this, we can actually figure this part out, which is essentially just using this completely together by itself. Okay, and that's what would lead us directly into Bayes' theorem. So I'm not going to go into full Bayes' theorem just because the curriculum doesn't go into this time. We can talk a lot about like how to actually apply this. One thing, for example, is probably one of the first machine learning algorithms. I don't actually know if you would classify as machine learning algorithm, but I think I would in this case. Is something called naive Bayes. So naive Bayes, if you guys are curious, I think we'll actually talk about this in a little bit later section, not in this module, but next module. But naive Bayes basically allows us to use the fact that we have information and update our belief of the full system. Basically, it's like, how do you know a coin is 50-50 by flipping it, right? Like, you know, like how do you know it's going to be 50 heads, 50 tails, 50% of the time heads, 50% tails. The way you do that is literally just flip the coin. And the more times you flip that coin, the more likely you're able to say, well, okay, it looks like it's 50%, you know, heads, tails. And you have to do this over and over again. And the more information you have, the more confident you are in doing this. But the point is basically you're using information that you actually have to update your beliefs. And that's what naive Bayes essentially does. It does some cool tricks with probability of A. And this is actually one of the first, I don't know, you guys probably recall when spam for email was really, really bad. And spam now for email is relatively tame. Like, I think it catches most stuff. If you use Gmail or any other major, I mean, not even major, like I think almost every email service in this case does a pretty good job catching spam. The big reason why is because naive Bayes was actually applied to that system. It's a really classic one that people talk about as an example for naive Bayes because it works so well at classifying what is spam and what isn't spam. And it's all done basically through this math. Okay. And then, so that's I kind of went from the product rule down into Bayes' rule, or Bayes' theorem. There's also the chain rule, which essentially is just the product rule. It's like the generalized product rule, but you have multiple parts. So essentially you kind of lump, you know, A and B together, and then just consider, like, if you can consider this by itself, it's like this D in C. And then basically you can kind of build up this probability, this rule. So I don't really like saying this is a rule because really it's just this rule. Okay, just applied multiple times. But the curriculum also shows this part too. So just know that you can break it down even further. And the whole point of us being able to break this down is so we can actually get the Bayes rule, because Bayes rule is probably what we'll likely care about. Okay. All right. I know I got a lot of drawings on this, so I'll clear this up. Any questions? Any kind of thoughts or concerns right now? Sound pretty good? Okay. Thumbs up for right now. Thumbs down for understanding. Yeah, I see a little like thumbs up, but probably more sideways. And that's where, you know, it's helpful to kind of go through. There's definitely a lab that will kind of guide through, and I think as you kind of practice through and see some examples, it gets easier and easier to kind of get through. The curriculum actually does a really great job, I think, going through a lot of different examples, even outside of the lab. So definitely take your time to go through that. This is my suggestion. Okay, so last thing I just want to note is that partitioning, I didn't even write it apart on there because I think we actually have it in here. But partitioning, basically, you're essentially splitting up the sample space into different parts. And so I think, again, the curriculum does a good job, so I'm not going to go full into it, especially this being a review. But under the law of total probability, let's see if this will load quick enough. If not, I can open it here. Give it a second. But there's a good job of actually explaining how you partition the sample space. And basically, you're just saying, okay, we have an event B, for example, and we're splitting it up into multiple parts to say, okay, well, what's the probability of B happening given A1, or probability of B happening given A2? And basically, we're partitioning it up. And it just allows you to consider those parts. And you'll see probability usually represented in this way. And the reason why is because probability in a lot of ways is just area. It's essentially equivalent to that. And you can think of this as a continuous space. Know that probability could be discrete, but usually we can consider probability in a continuous space, so it allows us to kind of consider those parts. Okay. And again, the law of total probability is kind of what I just described in Bayes' theorem. Essentially allows you to say, okay, well, the probability of A happening is just essentially A1 plus A plus 2, but we can figure this out by partitioning it with B. So it kind of allows us to do other calculation. Because a lot of times we won't know specifically the full probability, but we'll know specific conditions. We know what happens when this condition is true. So it allows us to do some extra calculation. Yeah, so I guess that kind of finishes up. I said that, like I said before, this is going to be relatively short. Any questions or anything that you guys want a little cleared up or anything like that? Okay. Cool. All right. So yeah, I would say, like, for example, you can see here these different examples. I think they do a great job. I'm trying to think if anything in particular I want to point out. Again, I think the curriculum does a pretty good job explaining everything. And a lot of the stuff is just, I think verbally, I don't know about you guys, but visually seeing this stuff in particular, I think is really useful because I think that's the way I absorb it the best. Saying it out loud, hearing PA, PB, stuff like this, it kind of gets mixed up in my head personally. And I think that's how most people go through it. Yeah, so I would say though, since you guys have seen section 8 of version 1, really the parts that you have to focus on, I believe, are just conditional probability, law of total probability, and then simulations are just the last part, which we've kind of already done a little bit with dice and stuff like this, which is basically it's another lab to kind of hone in those two topics together. Okay, cool. So with that, oh, before I forget, I wanted to show you guys that the resources I have here, because we switched over to version 1 to version 2, I split them up instead of the module numbers because I do have another cohort that kind of goes back and forth. And I thought, like, well, this might make sense. I broke it up into more like topic based. And so notice to find some of these parts, for example, the stuff that we talked about is more, what did we just talk about? Probability, right? So probability and stats. And as you can see here, for example, is that this is older. This is actually from version 2 later on, but it'd be in there if you want. Basically, the stuff we talked about is like under probability, combinatorics, conditional probability, and all this stuff. This way, it's a little bit easier to find by topic. I know it's not module, but in case we ever like change it over again, at least then you can find it by topic. Plus, in like the future, if you do consider using this kind of stuff to like kind of reference, you're not like, was that module 3 or module 4? And you're like, I don't remember what module 4 was. At least then you know, oh, well, I know it's probability. I can go find it in there. Okay, cool. All right, so with that then, I'll go ahead and stop recording.